Okay. Anyone have questions over anything? No? Okay, so we almost finished 11.5 last time, correct? We didn't quite get there. We still needed to talk about implicit differentiation. You remember we were doing the tree diagrams and the chain rule and all that last class? Okay. So if let's say we are faced with a problem like this. X cubed plus y cubed plus z cubed plus 6xyz equals 1. And we want to find the partial of z with respect to x or partial of z with respect to y. Then this is not falling into that category of needing to draw out a tree diagram because we have one equation only. We have a relationship between x, y, and z, and that's it. So we don't have any other conditions like, well, let me see, last class, bring that up. So in case you forgot, like something like this where we had z is somehow connected to x and y, but then x is somehow connected to r and s. The y is also connected to r and s. In this case, we did the tree, right? But today, for this example, all we have is one equation. So we could try and isolate z and then do partial derivatives the way that we've done before. So if we can get z isolated, we'll be in business. And in this case, we could, right? We could just take these two to the other side, right? And then, well, then what would you do? Because you'd have a z cubed and a z here. How would you get z exactly by itself? It wouldn't be that clean, would it? So when we can't, we use implicit differentiation. The last part of this section is just a formula. Now, in the notes that you may have printed off online, I know some of you had them, right? There might be a typo, so when I get to it, I'll point it out. Here's the way it's going to work. So we'll come back to this in a second, all right? Suppose we have capital F of x, y, z equals 0. In other words, we have an equation where we can move everything to one side, set it equal to 0, and the left side is some function, capital F, of x, y, z. So on the left side, you see a bunch of terms possibly with x's, y's, and z's in them. Okay, if that's the case, all right, then the partial of z with respect to x will be equal to negative partial of f with respect to x divided by the partial of f with respect to z. Okay, this is a formula right here. It's in the book, but just put it here. And we have another formula. The partial of z with respect to y, and this is the one that has the typo, so check your notes, is partial of f with respect to y over partial of f with respect to z. I believe in the notes, is there an x there on that one also? Who has the notes? Anyone? Is that on there? Two formulas. Can I see it? Did it get corrected? Let's see here. So that one and then this one. Okay, yeah, it is corrected. All this does is it just cuts down on the amount of time it takes us to do this. All right. And the book goes through and explains, how you can come up with these formulas, so I'm not going to. So let's just apply it to this problem. Go back up to this and continue. So what is capital F for us up here? What's capital F? The left side, correct? But we need to move this over. Technically, we need to move that over. It's not going to affect anything because it's a constant. But to be precise, let's go ahead and move all terms to the left side of that equation. That's our capital F. So what we're doing is we're calling the left side of this equation a function. And so we're not really dealing with the equation anymore. And now, to find the partial of z with respect to x, I need to use this formula here. So what would the partial of capital F with respect to x be? So just come through here and take the derivative with respect to x, which means you treat y and z constant. All right, so what is the derivative of x cubed? 3x squared. Derivative of y cubed? 0. Derivative of z cubed? 0. Derivative of this right here, 6yz, so plus 6yz. Are we done? That's it on this. That's it for the partial with respect to x, right? Now, divide that by, and I forgot my negative sign. Let me put that negative out here. Partial of f with respect to z. So now we treat x and y like constants. So what will we get? Derivative of x cubed is 0, right? Y cubed, 0. Derivative of z cubed, 3z squared. And then plus, the last piece here, 6xy. That's it. We're done. So all it is a shortcut formula. I just want to show you how to apply it one time. Are there any questions on that? Make sure there's nothing else in here I wanted to mention. Okay, I'll leave this one for you. If you wanted to do this one, I'll let you do that one on your own. Okay, we're going to start a new section today, 11.6. I'm trying to get as far as I can. I know we're a little bit ahead on the schedule. I'm trying to get as far as I can because 11.8 is going to take a while, and the more time we have for it, the better. So we will keep pushing on. All right, 11.6, the directional derivative in the gradient vector. So let's look at a surface. Okay, I'm going to show you. We talked about this already, but let me get first to the picture, and then I'll go back to this. Where is it? Sorry, I got to bring this thing up. Let's start this over. All right. We looked at a picture very similar to this when we first started talking about partial derivatives. Remember that the partial derivative gave you the slope of the tangent line when you actually just pointed in one direction, right? The only directions that we are allowed to point, this is where I come out here and walked out here. I said you could point. One direction would be parallel to the y-axis, and the other direction would be parallel to the x-axis. And those were the only two directions we were allowed to point, right? That's what the partial derivatives gave us, right? Okay, but now instead what we're going to do, we're going to look at, man, this projector is junk. Okay, here we go. We have, again, this idea of taking a surface, and let me pull my surface out of here. And when I cut that surface, remember it intersected in this curve? And then I could talk about the derivative there. Yes? Now, which one would this be? What does it look like? If I turn this to the side, looks like my direction that I'm pointing is parallel to which axis? It looks like the x. Let me see here. Yeah, it is. It's parallel to the x-axis. So what am I holding constant here? Y? So this is the partial with respect to x, isn't it? Yes? Now, if I change my direction, now I'm holding my x constant, right? My x is being held constant here. And now this would give me the partial with respect to y, right? Notice there's two answers here. Let me see if I can get this on the screen. So this is it. Don't worry about all this notation up here yet. But the answer right now is -1. So the slope of this tangent line is -1. If I were to rotate back the other way where we started, what was the slope of the tangent line? Looks like +1. So it's different depending on which way I point. Today, we are not going to necessarily have to point parallel to the x-axis or parallel to the y-axis. We are now going to point in any direction we want. So if I go and slide this around now and to turn it, I can go in any direction, right? So what would be the slope there? Well, it looks like in that direction it's really small, right? It's like 0.088. So the direction which I point determines what my tangent line will be, what that slope will be. So the question becomes, how do we actually compute this tangent line, right? How do we do that partial? Does it make sense that it would be some combination of the partial with respect to x and the partial with respect to y? It somehow has to do with the two directions itself, some combination of those. So I'll bring my surface in here again. Let me move around on that surface. Let me go to a different point. Okay. So I've kind of like come up over that hill. You can kind of see it there. All right. And what about this point? See how close I am. You see where I'm trying to get to? I'm trying to get to the top, right? If I were at that top point, right? If I were at that top point, then what would the slope of the tangent line be in any direction? 0, wouldn't it? In any direction. That's going to come later. That's going to be in the next section. But first we need to get our heads around what does this mean? How do we actually calculate this, this new thing called the directional derivative? So if we look at that, we can pick any point in the domain and get a point on the surface. At that point in the surface, we can point in any direction, right? In that direction, there is a tangent line. Slope of that tangent line depends on the direction we point. Now, the question becomes, when we say direction, what are we talking about? So you see that red arrow on the bottom? Remember, this is our x-axis, this is our y-axis. If I take that surface out, and we look at this from the top, do you see that the plane where we're intersecting, the direction we're pointing in, is parallel to this vector? Yes? So that red vector on the ground is going to be our direction. Right now, if this is the x-axis and this is the y-axis, my direction is actually, let me bring it to 0. Does it make sense to you that this would be 0, the direction is 0? Because the x-axis isn't to the right always been 0 degrees, right? So direction for us is going to be measured from x-axis, parallel to x-axis is 0, and then as we rotate, it will be our standard angle. So if we go counterclockwise, that's too far. How about I go like that. So I have some positive radian degree, or some positive radian measure, and so I'm going counterclockwise around here. Yes? Come on. So again, if we pick a point, we're somewhere on the surface, point in some direction, and then there's a slope of a tangent line. So if z equals f of x is our surface, so there we have an actual surface defined, then f has a directional derivative in the direction of the unit vector. This is a big word right now, okay? We need to remember this. In the direction of the unit vector u equals ab, and this is the actual notation we use. It's the derivative, okay? It's the derivative in the direction of u. Before, when we were doing partial derivatives, we did like capital D subscript little x. That meant the partial with respect to x. Big D little y meant partial with respect to y. If we put big D subscript the vector u, then that means we're looking at the slope of the tangent line in that particular direction that that vector u points in. Now, u is a two-dimensional vector, isn't it? Okay, that means u lives in two space, so it's down on our domain. It's that red vector. Okay, that's what the u is. But the red vector we use in this formula must be a unit vector. Okay, so if someone gives you a vector, says, hey, point in this direction, you can use this formula as long as that vector has a length of 1. What if they give you a vector that's not length of 1? You can make it length of 1, right? But you have to remember that step, right? Remember, if someone gives you a vector, you can always make it unit length by dividing it by its own length. So that's a tricky point. It gets a lot of people on these problems. They forget to convert it to a unit vector. So if you have that unit vector, then the slope of the tangent line is given by this formula. And check out what it is. This little f subscript x is the partial with respect to x, isn't it? But you're scaling it by how much? By a. A is the x component of this vector. And then you're saying plus b times the partial with respect to y. So you're just scaling the partial with respect to y and then adding the two together. Does it make sense that this would work? What if you wanted to point down the x-axis? Okay, if you want to point parallel to the x-axis. Let's say that I have a surface, I'm looking at it from the top, and I want you to give me the partial derivative pointed in that direction. That's the partial with respect to what? X, right? Because that's holding y constant. Give me a vector that points in that direction, and if you can, please make it have length 1. What would be u here? That would point us down the x-axis. 1, 0, the vector 1, 0, do you all agree? That's a vector that points in the direction of the x-axis, has a length of 1. If you go back to this formula and you plug in 1, 0 here, what do you get? 1 here, 0 here, 0 kills that, right? And what do you get? The partial with respect to x, don't you? Which is exactly what we did before. And then what if we wanted to point up and down? Right? If we want to point this direction, I could make my vector 0, 1, but then that's just the partial with respect to y. Do you see that? It's really like this formula is a more it's a generalization of the partials we did before. We start out with the partials and we say, oh, you can only go in the direction of x or y, but now we're saying, no, you can really go in any direction, and that's where the original partials came from. Make sense? All right, so here's an example. If f of xy equals x cubed minus 3xy plus 4y squared, then find the directional derivative at the point 1, 2 in the direction of a vector making the angle pi over 6 with the x-axis. All right, here we go. Example 1. So we have, first of all, z equals f of x, y equals x cubed minus 3xy plus 4y squared. So we have a surface, right? This is a surface. Somewhere on that surface, we want to go to a specific point on that surface, right? The point we want to go to is the point f of 1, 2. What would we get if we plug in f of 1, 2 here? We get 1 minus 6 plus 16, right? Which would give us 11, yes? So basically, I'm just trying to get an idea of what's going on here. I have a three-dimensional graph. Here's x, here's y, here's z. I'm going out 1 on the x-axis. I'm going out 2 on the y-axis. That puts me here. And then when I plug that point in to the function, it comes out, and I'm up here at some point, and that's 11 units high, right? That's on the surface. Are y'all with me? I would like to be standing on that surface right now, and I'd like for us to point in the direction, okay, in the direction of a vector making an angle of pi over 6 with the x-axis. So that would be like pi over 6. I'm going to the origin here. Y'all see me here at the origin? Pi over 6 would be like somewhere in this direction. Do y'all agree? Which means that at this point, it would be the same direction. All I'm doing is moving that vector and saying if I were to look straight down at the ground, that should be running. We should have, like if this were a straight line coming out here, this angle in here should be pi over 6, shouldn't it? Okay, now what I'm going to do is instead of trying to draw a three-dimensional, I'm just going to draw a two-dimensional picture with the x and the y. I went out 1, I went up 2, here's where I am. I know that the direction I need to point in has to give me an angle here of pi over 6. So what I need to do is come up with a vector that points in that direction, but has a length of 1, right? So how can I come up with a vector that points in that direction and has a length of 1? Pi over 6 should be familiar to you, right? Pi over 6 is one of those common angles off our unit circle. Our unit circle has a radius of 1. And this is pi over 6. What's the x and y coordinate at that point? Uh-oh. Root 3 over 2 and 1/2, right? That's the x and y coordinate on the unit circle for that angle, which means we can use these coordinates as our components of our vector, right? If I call u the vector root 3 over 2, 1/2, right? If that's my u, does everyone agree that that points in the direction of pi over 6? Yes. And does everyone agree it has unit length? You just take, you could check it, but it's from where it came from. It's obviously on the unit circle. The length should be 1, but you could check it. You just take each one of these and square them, and then add them together and then take square root, and you should get 1, right? So that is a unit vector, points in that direction. That's what I'm going to use. So remember, I'm trying to use this formula right here. In order to use it, I need to know what u is, which I've got, right? I also need to figure out what the partial with respect to x is and the partial with respect to y. I need to figure those two things out also. So let me go ahead and do that now. What is the partial of this thing with respect to x? So come back up here. What's the partial of this with respect to x? 3x squared, right? Minus 3y. 3x squared minus 3y. What's the partial of this thing with respect to y? What do we got? Negative 3x plus 8y, right? So do I have everything I need now to plug it in and get an answer? I needed the partial with respect to x. I've got it. I needed a. I've got it. I needed the partial with respect to y. I've got it. I need b. I've got it. Now I also need what x and y are. What are x and y in this problem? Where I'm standing, right? 1, 2. So I should probably go and just plug it all in and be done. I'll do the work right here. What's the partial of f with respect to y, with respect to x at 1, 2? So I'm taking this and plugging in 1 for x and 2 for y. What do we get? Negative 3. And then using the same idea, partial with respect to y at 1, 2 should be, what's that, 16 take away 3, 13, right? I'm ready for my final answer. Here it is. The partial derivative, or the directional derivative in the direction of u at the point 1, 2, f of 1, 2. I'm just rewriting this right here, okay? Should be equal to a, which is root 3 over 2, times the partial of f with respect to x at the point 1, 2, which was what? Negative 3, and then plus now b, which is 1/2, then times the partial of f with respect to y at the point 1, 2, which is 13, which gives you negative 3 root 3 over 2 plus 13/2. And then you could get that on your calculator. If we wanted an approximate answer, you get a decimal. If you get if you leave it like that, it's the exact answer. Is this a positive or negative number? It's positive, right? That's a positive number. So that means that if we were to do this and actually go out to that surface and stand there and point in that direction, the surface should actually be going which way in that direction? Up, right? Should be going up. Make sense? Now let's see, is that the actual surface I had? Hold on. No, I have a bunch of different surfaces here. No, I don't have that one. All right, let's try another one here. By the way, I got your take-home test, whatever quizzes. I didn't get all of them till today, so I'll start grading those probably today and tomorrow. So I won't have those back. Hopefully you'll get them on Wednesday. All right. All right, this problem, different surface, right? Natural log x squared plus y squared. Then find the directional derivative at the point 2, 1 in the direction of the vector u. So what's the difference between this problem and the last one? I mean, obviously the function's different, but what's also different? I give you u, right? Instead of giving you an angle, I just tell you what u is. But do you see an issue? What's that? It's not a unit vector, that's correct. the u that you're given, although it does give you a direction to point, it's not a unit vector. So if I look from the top again, if this is x and y, this time I'm going out 2 on the x-axis and 1 on the y-axis, and then there's a point, and I'm going up onto the surface, wherever it is, right? But if you're looking at the ground, I want to be pointing in the direction of the vector, what, -1, 2? So from this point, if I go -1 and then 2 up, I'm pointing in this direction. Do y'all see that? Problem is that vector does not have unit length. So even though I called it u, it was more to trick you into thinking you could use it, because what you actually have to do is make it unit length. So to make it unit length, we're going to divide it by its own length. So what is the length of that vector? √5. So I'm going to start a new vector. I'm going to call it v instead of u. V is equal to -1 over √5, 2 over √5, right? That's all right? And now we're actually going to calculate the directional derivative in the direction of v instead of u, because v does qualify as being a unit vector. This is unit. We also need some partials, right? What's the partial of f with respect to x? What's partial of f with respect to x? What is it? 1 over x squared plus y squared times the derivative of what's in there, 2x. So let's just put 2x over x squared plus y squared. And what is the partial of f with respect to y? 2y over x squared plus y squared. And now I actually need to plug in the value to get the value at the point that I'm standing. So I'm going to evaluate this at the point 2, 1, right? So if I plug in 2, I get 4 over 5. And over here, if I plug in 2, 1, I get 2 over 5. Agreed? So that's all I need to write it all out. The derivative in the direction of v, not u, of f at the point 2, 1 would be equal to -1 over √5, that's my a, times 4/5, plus my b, which is 2 over √5, times 2/5. What is this? What is it? -4 over 5√5 plus 4 over 5√5, which is 0. It's 0. Which means that we have a flat tangent line, right? Does that necessarily mean that I am at the highest point of a surface or the lowest point of the surface? Is that the way it was in Cal 1? If your derivative was 0, did that mean that you were at the highest or lowest? Not necessarily, right? But it was a good idea to see maybe it was. Look, like in Cal 1, if I draw that, obviously, if you go to this point and the slope of tangent line is 0, you're at a maximum, right? A local max. Or if you were to go like this, here at this point, slope of tangent line there would be 0 also, so you'd be at a minimum. But there was the possibility that your graph did something like that, where you go to this point right here and the slope of your tangent line is 0, but you're not at a maximum or a minimum, right? And you could also have something like a cusp, where you would have a minimum, but your derivative wasn't 0 there. Your derivative was actually what? Undefined. So we learned in Cal 1 that just figuring out where the derivative is 0 is not enough to figure out where the max and mins are. But they sure as heck do give us some information, right? All that we did was show that in this one particular direction, if you were standing there, the slope would be 0 in that direction. You might turn a little bit to the right and the graph starts going up. That could be the case. All right, any questions on that, computation-wise? It's pretty straightforward, right? Just got to keep track of things, make sure your u is a unit vector, plug and chug. All right, now we define what's called the gradient vector. Notice that in this formula, since we have a times this partial plus b times this partial, we could, if we wanted to, rewrite it this way. Remember how you compute a dot product of two vectors? If you take two vectors and dot them, you do the first component times the first component plus the second component times the second component. And if I do that, this partial with respect to x times a would be this first part. This partial with respect to y times b would be the second part. So we could, if we wanted to, rewrite the directional derivative as a dot product. Yes? That's very important for where we're headed. So that's just notation. Now, some more notation. The gradient vector, right? The gradient vector is defined to be that vector right here. It's the vector that's made up, the components of the vector are just the partial derivatives of the function. Anytime you take a function and you create a vector which is made up, its components are the partials, then we call it the gradient vector. All right? This is the notation, del f, or just del f of xy, or del f, and then you just put partial with respect to x, partial with respect to y in there like that. These all mean the same thing. So anytime someone gives you a function of two variables, you can always find the gradient vector, which is just the partials, right? That's all it is. So we'll do that one real quick. If we have a function f of xy equals e to the xy, we want to find the gradient vector. In other words, we want to find del f, right? That's the way I'll write it in class. Well, by definition, this is just the vector, where the first component is the partial of f with respect to x, and the second component is partial with respect to y. So what is the partial of f with respect to x? You have to use some chain rule there, don't you? What's the derivative of e to anything? Itself, but then times derivative of what's up there. What's derivative of what's up there with respect to x? Y. So can I just write y e to the xy? Right? And then when you do the partial with respect to y, it's the exact same thing, except an x pops out. So we have x e to the xy. That is the gradient vector. That's it right there. Does everyone understand? If someone gives you a function of two variables and asks you to find the gradient, all you're really doing is finding the two partials and putting them in a vector. Yes? All right. Now, everything we just did can be extended to three-dimensional, not three-dimensional space, but three-dimensional functions, where your function's taking on three variables instead, taking in three variables instead of just two. Now, the problem with this for us is that we don't have a way of visualizing these functions, right? If I say, hey, graph this function, you could start plugging points in and trying to figure out what it looks like three-dimensionally, and it would be a surface. If someone asks you to draw this function, you can't do it, right? On a piece of paper, you wouldn't be able to. So, but everything we just did extends here. So if you have a function of x, y, and z, then the directional derivative in the direction of the unit vector, again, unit vector, but instead of AB, it's ABC, is given by this. So the A is in front of the partial with respect to x, then the B is in front of the partial with respect to y, but now you have a partial with respect to z, right? So there's your C in front of that. And further, you could break that up and make it look like a dot product again, and you could call the partials together in a vector the gradient. Or you could use that notation there. These are all the same, and this actually extends out if you have a function of 4 variables or 5 variables or 6 variables. It doesn't matter. You can always define the gradient. All right? Okay, so how about this one? Y'all look like y'all need to wake up. Why don't y'all do this one? Okay? See what you can get. Find the gradient vector, then find the directional derivative at that particular point in that direction. Sound like fun? Why don't y'all work together? We'll turn it in. All right? Yeah, sorry. You might want to start a new piece of paper. Let's turn it in as a quiz grade. But you can talk to each other, help each other out. Try not. We won't take up too much time in class for it, but. So let's see, the direction, or the derivative in the direction of the vector, you probably called it something other than u, so I'll call it v of f of x, y, z should be equal to 1 over, was it 1 over root 14? 1 over root 14 times the derivative, the gradient part of this was what? 1 over y plus z. So that should just be 1 over y was 1 and z was 1. Okay, so that. And then plus 2 over root 14. And then this should be negative x over 1 plus 1 squared. Then plus 3 over root 14. And then same thing, right? Negative 4 over 1 plus 1 squared. That should be it, but then you have to compute it all out. And what does it come out to be as an exact answer? Negative 9 over 2 root 14? That's a question. I'm not sure if anyone else got that. Yes, because you'll get 14 on the bottom, and then that'll hit the 2 and become 28. So you got negative 9 root 14 over 28? Yes, that's right. So this looks good. Okay? So now above this, remember, this is your A, this is the partial with respect to x, this is your B, this is your partial with respect to y, this is your C, this is your partial with respect to z, right? Those are your pieces of this. You're adding them together. Do I need to show any more detail, or are you okay? Anything else you want me to show you on this? All right. Yeah. You got to remember the quotient rule and things like that. Yeah. Yep. Okay, so where do we go with this now? Well, the whole idea well, one of the great things about the directional derivative is we can start talking about when is the directional derivative the greatest it can ever be. This actually turns out to be really amazing, I think. So imagine again that you're standing on a surface, right? Right now we can point in any direction and talk about the slope of the tangent line, right? Does it seem like it would be difficult to say, okay, look, go stand on some surface and tell me which way to point that would be the steepest descent? You know what I'm saying? Like there's a surface. Do you think it would be easy or hard to say, okay, go stand right there on that surface and then tell me which way to point so that you have the steepest rise? It seems like it might be challenging because you can point in any direction, can't you? Right? In any direction you can point. So how are you going to check every direction and say, oh yeah, that one's pretty steep, but over here this one's steeper? So it seems like it might be difficult to actually extrapolate like which direction to point in. But because well, let me go back up here. Remember that the dot product, when we first defined it, we said it was equal to the magnitude of u times magnitude of v times cosine of the angle between the two vectors. Right? So if I have two vectors and I want their dot product, it's the same as taking each of the vectors' length times the cosine of the angle between them. We know that the directional derivative, right? We could rewrite the directional derivative as a dot product. It's the dot of the gradient and the vector u. But that is the same as the length of the gradient vector times the length of u times cosine of the angle between them. And why is this just this? Because u is a unit vector, so the length of that's 1, so it's just that. The largest that this can ever be would be the magnitude of the gradient, right? Why? Well, because cosine, the biggest it can ever be is 1, right? And when is cosine 1? At what angle? At 0. At 0. This is a big deal here. Because what it tells us is that in order for this dot product to be the biggest it can ever be, we need the angle between these two vectors to be what? 0. Now remember, the gradient of f is the gradient of f, right? Like someone gives you a function, the gradient is the gradient. The direction they tell you to point is what we're trying to figure out, right? We're trying to figure out which way do you point. Well, this tells me that to make this the biggest it can ever be, I need to point in the direction that gives me an angle of 0 with the gradient, which means I need to point in the direction of the gradient, which means the gradient direction tells you exactly which way to point to get the maximum ascent. And that's the major result, okay? Which means that the angle between the gradient and the u must be 0 to attain the largest directional derivative. So this is how we maximize the directional derivative. The maximum value of the directional derivative, so the steepest descent that you could possibly get at a point, the maximum value of it, the steepest descent, is the magnitude of the gradient. That's the biggest you'll ever be able to be. And it occurs exactly when we point in the same direction as the gradient itself. So the gradient's a vector, right? So therefore we can look at it as a direction. And then its magnitude is a number. So the length of it is the actual directional derivative. So how can we use that? Well, if f of xy equals sine x minus y plus cosine x, then find, part A, the direction as an angle of the maximum rate of change at the point 0, 0. And then part B, what is the maximum rate of change at that point? Okay, so here's what's happening. We have a surface. We are going to the point 0, 0. We're going up somewhere on this surface. I don't know what this surface is doing, okay? I'm just going to act like I do. There's my surface. Somewhere up here on this surface at the origin, I'm at some point, right, on that surface up there. I'm actually on the z-axis, right? Okay, so I'm standing up there, and the question is, which way do I point so that I go the steepest ascent, and actually, how steep is it? Those two questions can be answered by simply looking at the gradient. That's all we have to look at. So what is the gradient of this particular surface? Do I need to write it all down again? Here's what our surface was. F of xy was sine x minus y plus cosine x. The gradient of this is equal to the partial with respect to x, which would just be cosine x minus y minus sine x. So I'm just taking the derivative of this with respect to x. Derivative of sine of something is cosine of that something. Derivative of what's inside of here is just 1, right, with respect to x. And then derivative of cosine x is negative sine x when you're taking derivative with respect to x. So is that okay with the first component of my gradient? Then, now I need to take derivative with respect to y. So with respect to y in here, derivative of sine of something is itself, right? Or not sine, cosine of that, times the derivative of what's inside. What's derivative of what's inside here with respect to y? Negative 1. And then the derivative of cosine x with respect to y is 0. So that's it right there. That's my gradient. Now, the maximum directional derivative, okay, the maximum directional derivative is the magnitude of that gradient at the particular point you're talking about. So what is the magnitude of this gradient at that point 0, 0? Well, it's what's cosine of 0 minus 0, 0? So what's cosine of 0? 1. Minus what's sine of 0? 0. All right, what's cosine of 0? 1, and then times negative 1, so negative 1. I need the magnitude of that vector. What's the magnitude of that vector? Square root of 2. So what I've said is that if I'm up there standing on that surface, I start pointing out in different directions, the biggest ascent, the steepest I'm ever going to get is square root of 2. That's the largest it'll ever be. All right? Which direction is it going to happen? What direction? And I wanted does it say? Oh, I want the direction as an angle. So what direction do I point in? Well, didn't we say the direction was in the same direction as the gradient vector? Well, that means I point in this direction. So if you're looking at that on the ground, right? Here's my x, here's my y. That's the vector to the right one, down one, right? That's this vector, isn't it? Y'all agree? That's 1, negative 1. Now, I don't care about it being unit length. I don't need it, because all I'm trying to do is get a direction. All right? So what's the angle? As an angle, what is this? Remember, to the right 0. So I could say, what, negative 45 degrees? You could say negative pi over 4. Right? You could even come all the way around the other way. But I'm just going to say the angle, theta, is negative pi over 4. Yeah. Yeah, if this was not easy to see, you could use arctan to recover your angle. Yes. So if that was the vector like 3, 7 or something, you just go do some arctan stuff, and you'd be there. Just make sure if you're in degree mode on your calculator, you do degrees. And does everyone see that? There's a surface up here. I'm standing at the origin. I go up to the top of the surface. I point no, x-axis was this way, right? So I'm pointing this way. If I rotate negative 45 degrees and I start going in that direction, I will start increasing at a rate, instantaneous rate of square root of 2. Any other direction I point, the increase will not be that much. That's the steepest ascent. Okay? Now, for those of you who know anything about topography, where they have like topographical maps where they have contour lines, this is basically where you can say, all right, look, I want to find a path that's going to be the shortest path to the top of the mountain. Well, that means you want your gradient, you want to always follow the gradient vector, don't you? You want to go in that direction, then when you get to the next point, to the next direction, then you find this path, and that path would actually run perpendicular to all your contour lines, and you go up the mountain or come down the mountain that way. Now, if you want to go and there's a mountain, and you want to walk around the mountain without going up or down elevation, then you want your gradient vector to basically be 0 the whole time. So you walk around the mountain, but you never go up or down. All of it's connected to the gradient, though, gradient vector. All right. You get the idea? You can do this one, I think? See how much more we have here. How about this? Remember I had you do that one problem just now in class, right? You're going to turn that in for a quiz. Throw that one on, we'll turn it in next time, all right? Beginning of class. Put example 6 on there also. Don't do it now. We're going to keep moving on. I want to try and finish this section. Example 6, yes, from 11.6. All right. All of these concepts extend, like I said, to functions of more than 2 variables. If I have a function f of x, y, z, which is equal to x sine y, z, part A says find the directional derivative at a point in a direction. Then find the magnitude of the gradient at that point, and then it says which of these should be larger. Can you answer part C yet? B should be larger, right? Because the largest directional derivative you'll ever get is the magnitude of the gradient at that point. There's no directional derivative that'll be bigger. So part B should be the larger one. So part A is just, bless you, is just a computation. Part B is using the power of the fact that the maximum directional derivative occurs when you point in the direction of the gradient. So before I actually do this one, let's talk a little bit about this. F of x, y, z is not a surface in 3-dimensional space, right? So what in the heck, how can we get our heads around what's happening here? Here's the way I'll try and explain it. Your domain here is how many dimensions? Your domain, 3, right? So the first thing I need to do is actually go to a point in the domain. So let's say in the domain, I walk out 1, okay? I walk out 1, and then I go on the y-axis, I go 3, right? 1, 2, 3. And on the z-axis, I don't go anywhere. I'm going to the point 1, 3, 0. So at my feet right now, right? That's the point. That point gets plugged into a function. That function spits out a value, doesn't it? Let's actually figure out, is it an easy value to plug in? Yeah, it's 0, isn't it? You get 0 if you plug that point into that function. So imagine that what that is there is the measurement of the temperature at that point. Okay? So the 1, 3, 0, the point gives me a position. The function's value there gives me a temperature. Make sense? Now, since that's on the ground, can I move it up so you can act like we can see it a little bit better? Let's imagine that my backpack is my feet on the ground. Okay, so we're at the point 130 right here. Right there, the temperature is 0. Okay, so temperature is 0. Now, I'd like for us to point in the direction 1, 2, -1. So 1 would be this way, right? 2 would be this way. -1 would be down some. So I want to point downward in that direction. I want to start moving in that direction. And I want you to tell me the rate of change of temperature, right? So as I move instantaneously from here to there, what's that differential? What's the change in temperature in that direction? Understand? And then if I just sit there and say, okay, you're sitting there at that point, which way do you point so you get the maximum change in temperature? That would be the gradient, wouldn't it? The direction of the gradient would say, okay, look, there's different temperatures throughout the room. Point in that direction or whatever it is, and that you'll go and you'll change your temperature by the most in that direction. That's the best way you can kind of get your head around a function of 3 variables, is to just assign a value that makes sense to us, like temperature to it. Does that kind of help a little bit as far as visualizing what's happening? All right, the computation here. Let's go ahead and do this. So the function okay, part A, I want the directional derivative in the direction of the vector v, right? Is v a unit vector? No. So don't I need to make it a unit vector? Okay, so v, I'm going to call u is going to be v divided by its own length. That'll be my direction vector u. So that's the vector 1 over root 6, 2 over root 6, -1 over root 6. Y'all agree? That can be my unit vector. That gives me my A, my B, my C. Now I need the partials, right? So let's get the gradient. The gradient, what's the partial of that with respect to x up here? Sine yz, right? Sine yz. What's the partial of this with respect to y? So x is like a constant, so just bring it along for the ride. Derivative sine of something is cosine of that something. Derivative of the inside is, with respect to y though, z, right? And then the derivative of that with respect to z is x cosine yz, this time times y, yeah? Seems to me like perhaps these derivatives are the things that are going to hang you up a little bit here. Got to get comfortable with these derivatives though. What's that?
It's hard to just turn one variable off and treat it as constant. I guess it'd be easier if you just threw a number at that.
Well, let me ask you this. Have you done the homework out of the section for partial derivatives? That would probably help. Because then you would get used to it.
Yeah.
And that's the point. Right? So, what is it, 11.5? No. 11.3. So we're talking like 3 sections ago. What was the homework for 11.3? Does anyone have it written down? It's probably in my notes if I bring it up. 7 through 31 odd. That's all partial derivative problems. So At this point, there's no, it's a good thing the midterm's still, 2 weeks off? So you have 2 weeks to master that. But it should already be coming automatic to you at this point. Okay. Where was I? Trying to get this. There it is. All right, so what the heck do I do now? What was the point that we're looking at? We're at the point 130. So let's start figuring out what our gradient is at the point 130. What's sine of 3 times 0, 0? What's sine of 0? Okay. What's, see, this is 0 again, isn't it? 0 again. And then over here, see, 1. Cosine of 0 is 1. 3, so I think we get 3. Plug in 1 there. Plug in 0 here. Cosine 0 is 1, so we get 1, then times y, but y is 3. So that should be our gradient. Got it? Now, the directional derivative in the direction of the vector u of our function at 130 should be equal to our gradient dotted with u, which would just be what? Our gradient 0, 0, 3 dotted with u, but u was 1 over root 6, 2 over root 6, negative 1 over root 6. So negative 3 over root 6. What's that? So at this particular point, right, I'm sitting there and I said point in a certain direction, the change in temperature would be this much, negative 3 over root 6. But that's not the maximum rate of change that I would get. The maximum rate of change is the answer to part B. So for part B, how do I find my maximum rate of change? I need the magnitude of the gradient. Well, that's the magnitude of the vector 0, 0, 3, isn't it? I should say it's the magnitude of the gradient at the point 130. But that would be the magnitude of the vector 0, 0, 3, which would be 3. And what direction do I point? It doesn't ask this. It doesn't ask it, but what direction do I point to get that maximum rate of change of 3? Well, I point in the direction of the vector 0, 0, 3, right? Which would be, in this case, straight up, wouldn't it? 0, 0, 3 is straight up. So, do y'all understand what happened here? Okay. No matter what, any other direction you point, you're not going to get a rate of change of anything greater than 3. That's the most you'll ever get at that particular point. At a different point, it might be different, but at that point, that's the maximum. No, okay. The negative 3 over root 6 is the rate of change at that point when I told you what direction to point in, right? I told you what was the direction? 1, 2, negative 1. So I forced you to point in a certain direction, and then the rate of change was a certain value. This 3 is, if I don't tell you what direction to point, you actually can tell me what direction to point and what that rate of change would be, the maximum rate of change. In this case, the maximum rate of change that you'll ever get is going to be 3, and it will be exactly in the same direction as the gradient vector. So the gradient vector is pointing straight up. You go that direction, instantaneous rate of change is 3. Understand the difference? Okay. All right. Let's see here. What else do we got here? All right. Now, we had talked about tangent planes before, and we have now a final version of an equation for a tangent plane. So if you have an equation, well, let me go back. The equation that we had before this for the equation of a tangent plane required that we were looking at a surface as a function of 2 variables. In other words, let me see where it was. 11. I think it was 11.4. Yeah, it was 11.4. Remember this? Tangent planes, we had this if z equals f of x, y, so we have a surface, then we can find the equation of the tangent plane by using the partial with respect to x, partial with respect to y, and then a -1. And remember we said that the partials there, that was our normal vector of our plane? And we said the -1 would always be -1. The reason why this was -1 was because it was a surface, a function of 2 variables. What I'm about to show you says forget that. Forget that you have a function of 2 variables. Instead, imagine you have an equation that has x, y, and z in it equal to a constant, which is good because that includes all of our quadratic surfaces, ellipsoids, hyperboloids, all those things we studied back in 10.8, I think it was, all those weird shapes. We should be able to find the equation of tangent plane for any of those surfaces using this formula. Do you still see your normal vector in there? Remember the equation of a plane was a times, what was it? What's the equation of a plane? A times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0, right? That's the standard equation of a plane, where a, b, c is the normal vector. This is that equation, isn't it? But the a is the partial of the left side of that with respect to x, evaluated at the point, then the partial with respect to y, evaluated at the point, then the partial with respect to z, evaluated at that point. That gives you your normal vector. So that partial with respect to x, y, and z, that's your gradient, right? It's your gradient vector. So let me show you how this would work. Find the equation of the tangent plane to the ellipsoid. X squared over 9 plus y squared plus z squared over 25 equals 18 at the point -3, 4, 5. And we'll look at the picture first. You have an ellipsoid. You have a particular point on that ellipsoid. You see it? I want us to go to that point, and I actually want us to find the equation of that plane that is tangent to that ellipsoid. Now, you could not use the formula before from 11.4 because to use the equation or the formula for 11.4, this had to be written as f of x, y equals whatever. You'll see that it's not written that way. But because of what we just saw in the previous note, we should still be able to do this. So what I'm going to do, I'm going to write down x squared over 9 plus y squared plus z squared over 25 equals 18. -3, 4, 5 is the point that we're looking at. The left side of this, I'm going to call my capital F of x, y, z. And then equals the right side of this is our k. And that looks exactly like what this formula was saying right here. If we have left side as a function of 3 variables equals a constant, then this is what we should get for our equation of our plane. So I need a couple things. I need the gradient. So I need the partials, right? Partial of f with respect to x, y, and z. I'll do that first. Partial with respect to x is 2/9 x squared. Partial with respect to y is 2y. Partial with respect to z is 2/25 z. That derivative was pretty clean, wasn't it? Because this just has x's, just y's, just z's, so we didn't need any special rules. Yeah, I did. Thank you. So here, here, here. Now, in order to figure out, remember what we're trying to do is find the normal vector for this plane. We're trying to find the ABC. So we need this, we need the partials. Now we need to actually plug in this point into these partials. So I need the partial with respect to x at the point -3, 4, 5. But really, because the partial here with respect to x only has the x in it, I only have to worry about the -3. So -3 goes in there, becomes -2/3, right? Then we need partial with respect to y at the point -3, 4, 5. But only the 4 really matters here. We get an 8. And then the partial with respect to z at the point -3, 4, 5. Only the 5 matters. 2/5. Any questions on what I did there? Partial, partial, partial. Evaluate, evaluate, evaluate. And now I can go to this. So the equation of my plane should be -2/3 x minus what? -3, so x plus 3. And then plus 8 times y minus 4. And then finally 2/5 z minus 5 equals 0. That's the equation of the plane. It doesn't matter. It's a constant. So when you're taking the derivative really on you're really doing like a derivative on both sides, that's always going to go away to 0. One last thing, and then that's it for this section. We don't have to do a whole lot of work. This is almost the same exact problem. It says find the equation of the normal line to the tangent plane of the ellipsoid. That's the same ellipsoid. That's the same point, right? It wants the equation of the normal line to our plane. So let me try and remind you of what that is. If somebody gives you a plane, sheet of paper, right? The line that would, let's say, go through this point, that would be called the normal line, would be a line that's perpendicular, comes out the bottom also. Okay, so punches through the plane, but is perpendicular to the plane. So imagine that's like a perpendicular like that. Can you all kind of see that? It's perpendicular to the plane. Well, if we're asked to find the equation of the normal line, how do we find equations of lines in this class? What do we need to find the equation of a line? Point and direction. Do you have a point? Yes. Do you have a direction? What would be a great candidate for the direction of that line? Well, it's perpendicular to the plane, right? What else is perpendicular to a plane? The normal vector of the plane, right? Which is why they call it the normal line. So what would be a good candidate for the direction of that line? The normal vector of the plane. Do we know the normal vector of the plane? It's ABC, right? So there's not a whole lot of work to do here. But you have to understand you're getting the equation of a line instead of a plane right now. So here's what we do. We need a point and a direction. Okay, the point I have was already given to me, -3, 4, 5. I also need a direction, but I'm going to use the normal vector of this plane, which we found to be, well, I can tell you, it was, oh man, it was this right here, right? -2/3, 8 2/5, wasn't it? -2/3, 8 2/5. And now, the equation. Vector equation. R of t equals R naught, which is any point given on the line, which is rewritten as a vector, plus t times v, which is any vector which gives us a direction. So -2/3, 8 2/5. Everyone agree with that? We have R naught plus TV. V is the normal vector of the plane. R naught is a point that was given to us that we'll cross through. You could clean that up, but that's basically it right there. Questions on that? I gave you that take home, right, last time? I did? Okay, so see what you should be able to do on that. Anyone have it with them? You got it? Can I see it real quick? All right, so you should be able to do the first one. Well, you could do the first one at the end of last class. And, yeah, numbers 1 and 2 should be no problem now. Did I say when that was due? Next Monday? Yeah, okay, because, yeah, it's not, you can't do the third one yet. So by the end of next class, you'll be able to do the third one. Okay, the homework assignment for this is here, but I believe that might be the wrong page.
The quiz and the notes next class, right?
The quiz and the...
The one we did in class.
Yes, yes. The one that you did in class, and then example 6 is due at the beginning of next class, and then next Monday will be that take-home quiz, and then our test, which is a week, 2 weeks from today, you can turn in those bonus ones. Remember the bonus ones? Okay. This is actually page 667. I believe so. So look, do your homework. You shouldn't be this, I mean, it's not funny. I mean, I know it's funny, but it's not funny. You should not be that far behind. 11-3, and there's no excuse for it, okay? Because this class requires you to do your homework. Your exam in 2 weeks is going to cover problems like homework problems. And if you haven't been doing them, you're going to be in a dire situation. You really will be. But it's going to be a fair test. It'll be tests over stuff you should be doing. The problem that I find in a class like this is I give these take-home quizzes, and students say, okay, well, if I do that, I'm good. If I do that, I'm good. And that's all they focus their attention on. The homework is supposed to be being done at this whole time. This is not a class where I pick up homework. It's Calculus 3. I should not have to crack a whip to make you do your homework. You should know that you should have to do it. You know what I'm saying? Okay. That brings me to another point. I wanted to share something with you all.